In this session, I am going to continue with concept of isomerisms in coordination compounds. In the previous session, I talked about Werner's theory and first type of isomerism, structural isomerism. Second type is stereo isomerism. Let me move with stereo isomerism. Second one, stereo isomerism. In case of the previous type, structural isomerism, complexes having same molecular formula, but the structure or bond type is going to differ. And such kind of isomers are called structural isomers, and the phenomenon is called structural isomerism. Whereas in case of stereo isomerism, there will be difference in arrangement of ligands around the central metal atom in a space. Spatial arrangement of ligands is going to differ, and such kind of isomers are called stereo isomers. Let me write the keywords. They are supposed to differ in spatial arrangement of ligands. Spatial arrangement of ligands around central metal atom. Complexes having same molecular formula but differ in spatial arrangement of ligands around central metal atom in a coordination sphere is termed as stereo isomers, and the phenomenon is called stereo isomerism. So just to see the spell what I have written for the spatial arrangement in the space, all these structures, some are three-dimensional structures. So in the space, the arrangement of ligands will be different. Therefore, spatial arrangement of ligands. One example I am going to give you. If you consider geometry of octahedral shape, so 4 ligands will be present in 4 corners of the square, and one will be above the plane and one will be below the plane. This is how the spatial arrangement of ligands will be present, and they are going to differ in this concept, and therefore that we call it as a stereo isomerisms. In stereo isomerism, we have 2 different types. The first one is geometrical isomerism, and the second one is optical isomerism. Stereo isomerism, they are supposed to be classified into 2 types, geometrical isomerisms and one more is optical isomerism. So these 2 are the types of stereo isomerisms. One can easily say, so in these 2 kinds of isomerism, there will be spatial arrangement of ligands around the central metal atom that is going to arise. Because of that, we get different isomers with the same molecular formula. I will move with the first one, geometrical isomerism. The first type of stereo isomerism, geometrical isomerism. A type of stereo isomerism it is, and there will be spatial arrangement of ligands are going to differ. In this particular case, geometrical isomerism, of course the molecular formula will be same, but the position of ligands is going to be different. Some ligands are adjacent to each other, some ligands are opposite to each other. So based on position of the ligands, we have 2 subtypes in case of geometrical isomerism. One isomerism we call it as cis, and one more isomer we call it as trans. Therefore, geometric isomerism you can call it as a cis-trans isomerism also. Let me write the keyword. So complexes having same molecular formula but they differ in which ligands are adjacent or opposite to one another opposite to one another in coordination sphere, we call it as geometrical isomers, and the phenomenon is called geometrical isomerism. So very important part is whether the ligands are adjacent to each other or they are opposite to each other. So based on that, we write the respective isomers as cis and trans. So first one is cis and the second one is trans. So first one cis. In this case, identical ligands are adjacent. Identical ligands are adjacent to each other. And one more type of isomer is trans. You can guess what would be the arrangement in this case. In this particular trans isomer, identical ligands are opposite to each other. So based on the position of ligands, whether they are adjacent to each other or opposite to each other, we name the geometrical isomers as cis isomer and trans isomer. Remember that if identical ligands, same kind of ligands, similar ligands, you can say identical ligands are adjacent to each other in a coordination sphere, the ligands which are same, if they are adjacent, then the isomer name will be cis isomer. If the identical ligands are opposite to each other, exactly opposite to each other, then such isomer is termed as a trans isomer. So geometrical isomerism is going to arise when there is a spatial arrangement of ligands, one is adjacent fashion and one more is opposite fashion, and based on that we call it as a cis trans isomerism also. So the molecules having same molecular formula or the complexes having same molecular formula but differ in which ligands are adjacent or opposite to one another in a coordination sphere are called geometrical isomers, and the phenomenon is called geometrical isomerism, and we have a cis and we have a trans. So if we have such kind of complexes where the coordination number is 4, where the coordination number is 6, such kind of complexes are going to show geometrical isomers. Coordination number 4, coordination number 6. Coordination number will be 4, then we have two chances of geometry. One is a tetrahedral and one more is a square planar. If the coordination number is 6, we have only one kind of geometry, that is octahedral. So out of these two, one is square planar and octahedral. Actually the complexes with the square planar are going to show geometrical isomerism but not a tetrahedral geometry. If the coordination number is 6 and we call it as the geometry, we call it as octahedral. So if you consider a complexes with coordination number 4 with a square planar geometry and coordination number 6 with octahedral geometry, they are supposed to show the geometrical isomerism. And then the question arises, if the coordination number is 4, as I said, two geometries are possible. One is a square planar and one more is a tetrahedral. Tetrahedral geometry with coordination number 4 does not show geometrical isomerism. The reason behind that is, in a tetrahedral geometry, the positions of ligands will be same. Since the positions of ligands around the central metal atom will be same, therefore there is no chance of differing in adjacent and opposite of the ligand around the central metal atom. Therefore coordination number 4 in particular square planar complexes only shows geometrical isomerism, and the coordination number 6 with the octahedral geometrical molecules are going to show geometrical isomerism. And in both cases, if the ligands are adjacent, we name it as cis. If the ligands are opposite, we name it as trans. And one more concept to remember, geometrical isomerism is going to arrive if you have the complex which is a heteroleptic complex. Homoleptic complex where we have a single kind of ligands. If we have single kinds of ligands, the position will be identical, therefore there is no chance of showing the geometrical isomerism, whereas heteroleptic complexes Complexes containing more than one different types of ligand, we call it as heteroleptic complexes. Such kind of complexes are going to show or possess a geometrical isomerism. That is the theory related to geometrical isomerism. Remember that how to name the particular example as a 6 and the particular example or the isomer as a trans, you need to know. In the examination they will mention one particular complex or coordination compound and you are supposed to draw the cis isomer of that and a trans isomer of that. So let me consider one example. We'll see the examples how we can write the isomers for geometrical as well as cis with respect to trans. The first example what I am going to consider here is observe the example what I am writing, PT NH3 2 times Cl2 and we have a square bracket over here and that is the coordination compound, the first example. So now if you observe here, now you can easily able to predict which one is central metal atom, ligand and all these things. PT is a central metal atom, NH3 is one ligand and Cl2 is one ligand. How many coordination number we are going to observe here? So central metal atom is PT which is surrounded by 2 NH3 and 2 Cl. So the coordination number is 4. As I said, a complex with coordination number 4 is going to show geometrical isomerism. In particular square planar geometry only. So here the geometry I am going to draw is of a square planar. I hope you know how actually the square planar geometry looks like. In the center we have central metal atom and the ligands, 4 ligands are going to occupy the 4 corners of this square and that we call it as a square planar. In a plane we are going to observe the central metal atom as well as the ligands. But since this compound shows geometrical isomerism, we can draw cis isomer and we can draw trans isomer based on the position of a ligand. So now observe here how I am going to draw the cis isomer and a trans isomer of this. So PT will be in the center, right? And we have 4 corners. So 1, 2 and 3 and 4. So these are the 4 corners. So this is one isomer what I am going to draw here and one more isomer I will be drawing here. So this is the 2 coordination bonds or the coordination number ligands we are supposed to write. So one is cis and one is trans. So now how to identify or how to draw the isomer of 6 and how to draw the isomer of trans, you just observe here. So we have totally 4 ligands, isn't it? 2 NH3 we have and 2 Cl we have. So 1, 2, 3, 4. 4 positions we have for where we are supposed to write the 4 ligands. And we cannot write randomly. We have a particular method and based on that we identify which one is cis and trans. What is the rule? I said if identical ligands are adjacent to each other then cis isomer we get. If identical ligands are opposite to each other, trans ligand we get. Identical ligand, same kind of ligands means Cl is one kind of ligand, NH3 1H3 is one kind of ligand. Identical ligands present on the same side we get cis. So first I am going to draw the isomer of cis. So NH3Cl2. So let me write one NH3 here and one more NH3 here and the one more kind of ligand is Cl and one more kind of ligand is Cl. So this is actually the cis isomer of this particular complex. So now why it is cis isomer? Because identical ligands are adjacent to each other. Identical ligands are adjacent to each other around a central metal atom. Therefore this particular isomer I call it as cis. I hope you got this one. Now we'll see how actually the trans isomer can be drawn. In a trans isomer, try to observe the identical ligands are exactly opposite. Identical ligands are exactly opposite. If I write NH3 here and the identical ligand I have to write opposite NH3 I will write here. NH3 I will write in this fashion because nitrogen is going to donate the lone pair of electrons. So therefore a bond between nitrogen and platinum. So therefore this NH3 I have written. So NH3 identical ligand, they are opposite. One more kind of ligand we have Cl. So one Cl I will write here and one more Cl I will write here. Since the identical ligands are exactly opposite, therefore this kind of isomer we call it as a trans isomer. So these two are geometrical isomers of this particular compound or cis trans isomers of this particular compound. So here in cis identical ligands are same side. You can write NH3 here, Cl here. Anyway, the same compound it is. And you can write Cl here, NH3 here, the same compound it is. But the rule has to be followed. In a cis identical ligands will be adjacent. In a trans identical ligand will be exactly opposite. Since we have 4 ligands, coordination number will be 4. Square planar complex. Therefore, I have drawn the geometry in terms of a square planar. One more example. So, next example, what I am going to consider here is CONH3 4 times Cl2 and we have a charge over here plus. So, this is cation complex actually, since on the coordination sphere we have a charge. So, now we are supposed to draw the isomers of this. Cobalt is a central metal atom, NH3 is one kind of ligand and Cl is one kind of ligand. Just observe here, as I said, the geometrical isomerism is going to shown by heteroleptic complexes here, more than one ligand. So NH3Cl, 2 different ligands. Here also NH3Cl, 2 different ligands we have. But the coordination number, observe here, we have 4 NH3 and 2 Cl2, 4 plus 2, 6. So the coordination number will be 6. So coordination number is 6 and that shows octahedral geometry. Octahedral geometry, how actually it looks, you need to remember that. So out of 6 ligands, 4 ligands will occupy the 4 corners of a square. And one ligand will be above the plane and one ligand will be below the plane. That is how actually octahedral geometry looks like. So let me draw the shape. So cobalt, you need to write capital C and small o only. If you write both as capital, that corresponds to carbon monoxide, the wrong structure that is. So CO, as I said, 4 will be in the one side. 4 ligands will be at the corners of the square. One ligand will be above the plane and one ligand will be below the plane. That is how we draw the octahedral geometry. And one more isomer I am supposed to draw. So let me draw the shape in that manner also. So this is a one bond and this is a one bond. And the third one and the fourth one will be above and one will be below. That is how actually the octahedral geometry looks like. Now the question arises how we are supposed to place 4 NH3 ligands and 2 Cl ligands. So first I am going to draw for the cis isomer and next I am going to draw it for the trans isomer. As we know, in case of cis, identical ligands are on the same side. So Cl2 we have. So you can write 2 Cl here, 2 Cl here, anywhere you write, but the identical ligand should be adjacent to each other. Therefore Cl I will write. So these two are the identical adjacent to each other. Since 2 Cl we have, I have written only 2. So remaining we have NH3 4. So 4 NH3 I will draw it for the remaining. So NH3 as I mentioned, there is a bond between nitrogen and cobalt. Therefore nitrogen you are supposed to write in this fashion. So NH3 all these are identical ligands. They are present adjacent to each other and Cl is also identical ligand, that is also present to each other. But in the previous example, that is a neutral complex. We don't have any charge over here. But in this particular example, we have a charge. Don't forget that. We need to mention the charge of that also. So how to mention? So above towards the right corner, you need to mention this kind of a symbol and here you need to write a plus, which indicates this particular complex is charged complex ion we have. And this kind of isomer, we call it as a cis isomer since identical ligands are present adjacent to each other. Now let me draw it for the trans. As we know, in case of trans, the identical ligands are exactly opposite. Now observe here, in this case identical ligands are opposite. Identical ligands are opposite. So here let me draw Cl first. If you write Cl here and one more Cl you write here, so anywhere you can consider. So let me consider Cl here, one more ligand exactly opposite I write, because if the ligands are opposite to each other, then that corresponds to trans isomer, and remaining I will be writing it for NH3. So this is NH3 and this is NH3, that is also trans, and here also NH3 I will write, and here also NH3 I will write, and this is a charged species. Therefore in this fashion plus I will write, since the identical ligands are opposite to each other, trans configuration I am going to write. So this is how for geometrical isomerism, whether it has coordination number 4 or whether it has coordination number 6, we are supposed to draw the cis isomer and trans isomer in this fashion. Remember, in a cis isomer, identical ligands are adjacent to each other, whereas in trans isomer, identical ligands are opposite to each other. Example number 3. Let me write the formula of the coordination complex Fe NH3 2 times, Cn 4 times, and the charge of this complex is minus an ionic complex it is. We'll write the geometrical isomers or cis trans isomers of this particular compound. Iron is a central metal atom, has to be written in the middle, and we have a 2 NH3 ligand and 4 Cn ligands. Two different ligands we have. One is NH3 and one more is Cn minus, cyanido ligand and amine ligand. But we have 2 NH3 and 4 Cn. Total number of ligands will be 6. Therefore, ultimately the coordination number will be also 6. And the geometry I am supposed to draw here is octahedral geometry. So, Fe in the middle, and we have 4 ligands at the 4 corners of the square. We have one ligand above and we have one ligand below. And one more, let me draw that. This is for the trans. I am going to draw here. So 4 corners of a square and one above the plane and one below the plane. Now we are supposed to write the ligands in such a position that in cis the ligand should be adjacent, whereas in case of trans the ligand should be of exactly opposite. So we have a 2 NH3, therefore NH3 I will be writing adjacent, so that the cis isomer I am going to get, and remaining is Cn. So Cn I will write here. So there is a bond between carbon and iron. So try to know that one. Cn minus is best example for ambidentate ligand. So if you write Cn in this fashion, if you write Cn here, N is going to be linked with iron. That is completely wrong concept, because in this Cn minus, carbon is also donor atom and nitrogen is also donor atom. In this particular given compound, the carbon of cyanido ion is going to donate lone pair of electrons. Therefore, carefully observe while writing the ligands here. Since identical ligands are present on the adjacent side, therefore this will be of the cis and the charge is the minus. You are supposed to mention that one. So this isomer is actually cis isomer. Now we'll see about the trans one. So in a trans, the ligands are exactly opposite. So here, if I write NH3 here and exactly opposite, I should write the one more ligand NH3 here, and remaining 4, let me write it for Cn. So this is a Cn and this is also Cn. So see here, Cn how I have written, because there is a bond between carbon and iron. This is a charged species, so the charge we need to write over here, and since the ligands are opposite manner, therefore this kind of isomer we call it as a trans isomer. One more example. So the next example I am going to consider here is cobalt with the Cl2 and En2. So fourth example, and we'll see in this particular example how we can write the cis trans isomers, geometrical isomers for this one. So cobalt is a central metal atom, and Cl we have a kind of ligand. Do you remember what actually En stands for? En stands for ethane 1,2-diamine. This belongs to bidentate ligands. Means in this structure En we have a 2 nitrogen which contains 2 lone pair of electrons. They are going to donate these lone pair of electrons towards this cobalt here. Therefore En is a bidentate ligand. So a slight change in the bonding we are supposed to consider if we have bidentate ligand. In the previous examples we have NH3, Cn and Cl. All these are monodentate ligand. Just we have used only one coordinate bond in that fashion. Whereas in case of bidentate ligand, the fashion of writing the bond will be completely different. So let me draw the structure of this particular compound of the isomers. Since the central metal atom is CO, and for the trans I will be writing the central metal atom is cobalt. So 2 and 2, totally 4 ligands we have. So 2 ligands, if they are adjacent, we call it as a cis isomer. So 2Cl I have written in this manner. So since Cl is monodentate, there is no change in that one. So in case of En, as I said, this belongs to bidentate ligand, ethane 1,2-diamine. So how you are supposed to draw that one? So observe here how I am supposed to draw. So this is how you are supposed to mention, and this kind of a curved lines you are supposed to draw, and here you write En. So this is the one En. One more En I am going to write here. So this is how I mention, and I will be writing En. So what this kind of the lines indicates, En is bidentate ligand that donates 2 lone pair of electrons towards the central metal atom. Therefore 2 lines we are supposed to represent it for bidentate ligand. In this particular example, En is bidentate ligand. Therefore instead of drawing single line, I have drawn in this fashion for bidentate ligand. Since the Cl are adjacent and En are also adjacent, we don't have any here, therefore this belongs to a category of isomer called cis isomer. Now we'll see for the trans how we are supposed to draw in this case. So CO will be the central atom, metal atom, and Cl, so one Cl I will write here, and in trans one more Cl, that should be exactly opposite. And we have a 2 bidentate ligand En. So one let me draw here. So this is the one En, right? And one more En I will be drawing here. So if you consider the bidentate ligand En, that is also exactly opposite. So this bidentate is opposite to En, and this Cl is opposite to Cl. Since the identical ligands are exactly opposite, therefore this belongs to a category called trans isomers. So the only change what you have to look over here is, we don't have any charges. I have not represented any charge. If it is charge, we are supposed to mention that whether it is plus or minus. So in this case, En is bidentate. This is how you are supposed to represent the coordination bond. It represents 2 lone pair of electrons is going to be given to cobalt from 2 nitrogens of ethane 1,2-diamine. So that is the example of bidentate ligand. So one more example I consider. And before moving with the examples, we have again one more kind of representation of isomers. So one is FAC we write, and one is MER we write. Instead of representing cis and trans, we have one more method of distinguishing the isomers, FAC and MER. FAC stands for facial and MER stands for meridional. So if the ligands arrangement is facial type, FAC we write. If the ligands arrangement is of a meridional type, of course identical ligands, and that we call it as a MER. So let me consider example, and we'll see how FAC can be predicted and MER can be predicted in case of geometrical isomers only. So let me write one example for that. So the example what I'm going to consider here for this is, so CO NH3, and that is of 3 times, and NO2 will be of the 3 times. So now we'll see how we can draw the geometrical isomers for this particular compound. Cobalt NH3 3 times and NO2 3 times we have, and this particular compound is going to show facial and meridional isomers instead of mentioning cis and trans isomers. So how actually this can be explained? So just observe here how I am supposed to draw the structure of this. So cobalt, of course, it is a central metal atom, and cobalt is a central metal atom for the both, facial and meridional. So 3 plus 3, 6 coordination number. Therefore octahedral geometry I am supposed to consider. Therefore octahedral geometry, let me consider the skeleton of octahedral geometry. So 4 at the corners and 1 above and 1 below. Let me draw it for here also. So 1 and 2, 3, 4, and 1 will be above and 1 will be below here. So now what I do, let me write the ligands, and later we'll see why actually it is facial and why actually it is meridional. So these are the bonds or the ligands to be written, 1 above and 1 below. So one kind of ligand, let me write here, NO2. I hope you know this NO2 is also ambidentate ligand. Nitrogen is also ligating atom and oxygen is also ligating atom. So N-nitrito, actually nitrogen we have first, that is going to link with cobalt. Therefore NO2 you are supposed to write here. So one more ligand will be here, NO2 I will write, and one more ligand I will write here, NO2. Okay, and ligand of NO2 let me write here. Okay, and NH3 we have. So NH3 I will be writing in the remaining places, NH3, NH3, and sorry, this I have written NO2, it is NH3. Yes. Sorry for that, this will be NH3. So now if you observe the structure, we have a 3 NO2 and we have a 3 NH3. And this particular isomer, I call it as a facial isomer. And one more structure I am going to draw here, and that is for the meridional. Let me write here, NO2 I will place here. And one more NO2 I will be placing here, one more NO2 I will place here, and remaining NH3 I am supposed to write here, NH3, NH3 and NH3. So this is actually the meridional isomer, how we are supposed to draw here. Now the question arises, why I have represented NO2, NO2 and NO2 here, and NO2, NO2, NO2 in this fashion, how to predict which one is facial and which one is meridional. Remember that in this particular example, we have two different kinds of ligands, NH3 and NO2. So if I consider NO2 as a ligand, in NO2 nitrogen is the ligating atom. So 3 nitrogen atoms of NO2, they are present on the faces of the octahedral. So I can represent here NO2, NO2 and NO2. And these identical NO2 ligands, they are present on the faces of the octahedron. So the faces, they are not exactly supposed to be present inside, on the faces. So on the faces you can draw in this fashion to identify facial. So 3 ligating atoms of ligand which are adjacent, they are present around the faces of the octahedron. Therefore that belongs to facial. Then what about the meridional or MER? If you observe here, so let me draw the dotted lines to identify you. So this is a 1 NO2, this is a 1 NO2 and this is the 1 NO2. So all these NO2 are around a meridian. They are around a meridian. What is actually the meridian? See here, in this particular case, see here, this is the one face. And you can draw here also, this will be the one face, and you can draw here also, this will be the one face. On the faces we will be getting the ligands, identical ligands, 3 ligating atoms of the ligands. Whereas in case of meridional, so this will be the one meridian. So here this is the one meridian and this will be the one meridian. Okay, so we can show both. I have shown only one to identify it better. So this will be the one meridian actually, and here what happens, we have 3 ligating atoms of nitrogen and they are supposed to join. So this is how, based on the position of ligands, 3 ligating atoms. So in the previous cases we have observed here, we have 4 ligands and 2 ligands. Here we have 2 ligands and 2 ligands. Whereas in this particular example, we have 3 ligands and 3 ligands. So based on that, we represent it as facial and we represent it as meridional. FAC, MER. In FAC, facial, on the faces we have NO2 ligands. In case of meridional, in the meridian we have NO2 ligand. That is how FAC, MER can also be predicted for the certain kind of coordination complexes. That is about geometrical isomerism. Second type of stereoisomerism, optical isomerism. Let me write here B, optical isomerism. So we are quite familiar with this term, optical activity, optical isomerism. Molecules or complexes which are non-superimposable mirror image isomers are said to be optical isomers, and the phenomenon is called optical isomerism. If you consider 2 complexes and they are mirror images to each other, and if you superimpose one over the another, they are not supposed to impose, and that we call it as optical isomers. So as we know, if I consider my left hand is one object and my right hand is one object, and if I place exactly a mirror in between these 2 objects, and they are exactly the mirror images, isn't it? So in the place of thumb, exactly mirror image, we have a thumb. Therefore these 2 objects are the chiral molecules, I can say. And if you place one over the another, and they are not exactly the same. So we have one group over here and we have one group over here. What I am going to say, my hands are chiral objects. Molecules or ions which are non-superimposable, we call it as chiral molecules. And we use one more well-known term, enantiomers also. And if you place such kind of chiral molecules in a polarimeter instrument, and if you pass plane polarized light, and these substances have capacity to rotate the plane polarized light. Some molecules rotate plane polarized light towards left, and such kind of molecules we call it as the levorotatory molecules. Some molecules rotate the plane polarized light towards the right side, and that we call it as the dextrorotatory. So in this case of optical isomerism, we are going to draw two isomer, one is of dextro and one more is of levo. Remember that dextro isomer will rotate the plane polarized light in the right hand side, whereas levo isomer rotates the plane polarized light towards the left hand side. Of course, these two must be the mirror images but not superimposed on one another. One more concept is, usually the bidentate ligands with the complexes of bidentate ligands is going to show the optical isomerisms. So this concept already we know, and now we'll come to particular examples for that. So let me write example for optical isomerisms. We'll see how actually dextro isomer and levo isomer can be drawn. So first example I will be considering cobalt we have, and En 3 times, and let me write it as the charge 3 plus we have. So as I said, bidentate ligand with octahedral geometry is going to going to show optical isomerism. Central metal atom is cobalt and En bidentate ligand. And in the previous example I have shown how to draw the bidentate ligand if you have in a isomer. So how many we have? 3 we have. So each bidentate ligand contains 2 lone pair of electrons, means 2 coordination bond. Totally 3 we have. 2 into 3, 6 actually will be the coordination number, octahedral geometry. But bidentate ligand we have 3 we are supposed to draw. So charge will be the 3 plus. So first let me draw the dextro isomer, and let me draw the one more levo isomer. Dextrorotatory substance and levorotatory substance is here. So try to know this dextro and levo are practical concept, experimental data they are. So one, if you know the dextrorotatory substances, the structure, and levo we can write by placing the mirror, or exactly the mirror image we can draw. So just observe here how I am supposed to draw this one. So cobalt we have in the middle. So En, and we know how we draw for the En. So this will be the one En, and this will be one more bidentate ligand, ethane 1,2-diamine, and one more, let me write here. So this will be one more ethane 1,2-diamine En. So this is dextro. So actually if you place this particular compound in a polarimeter instrument, and that rotates the plane polarized light towards right side, experimental data, therefore this is a dextro. And if you want to draw the levo structure, what you are supposed to consider? You are supposed to consider a mirror in between these two. So the dotted line what I am drawing here, this is a mirror, and the one more isomer should be exactly the mirror image of the dextro. So how actually the mirror image should be drawn? So exactly center middle we have a cobalt only. So in this position, right side we have En. Therefore here I am supposed to write one ethane 1,2-diamine here, and one more ethane 1,2-diamine. Let me draw here, and one ethane 1,2-diamine we have left side. Therefore mirror image, therefore one more ethane diamine I will be writing here. If this is dextro, and this should be definitely levorotatory molecule, levorotatory isomer it is. And if you consider these two exactly, and these two are mirror images to each other, and if you just replace this and if you place over here, and they are not exactly the superimposable, so non-superimposable mirror image isomers, enantiomers or optical isomers we call it as, and the phenomenon we call it as optical isomerism. This is the one example what I consider. Let me consider one more example to understand the optical isomer and the optical isomerism better. The second example what I am going to consider here is cis, and we have PT Cl2 En twice, and we have a charge over here. So the charge will be actually 2 plus. So now we'll draw the optical isomers for this one. So charge we have a 2 plus. In the previous example also we have a charge. I forgot to mention here. Sorry, it is compulsory to mention this charge. So charge you are supposed to mention. So 3 plus here. I apologize for not writing the charges. It is compulsory. Otherwise you are supposed to lose the marks if you won't mention the charge here. So cis PT Cl2 En twice 2 plus we have. So they have mentioned whether the particular complex or coordination compound is cis or trans. Cis we have. So try to know that one. Cis is a word to be used when ligands, identical ligands are adjacent to each other. So you are supposed to draw a diagram in such a manner that the identical ligands should be adjacent to each other. How you are supposed to draw that? So let me consider that. So of course the platinum, the central metal atom will be the platinum. So let me write here. So Cl2 we have one Cl I will write here, and one more Cl I will write here. Since two Cls are adjacent, therefore that is a cis. That is going to be suitable the structure what I am going to draw it for. So one more ligand we have En, which is a bidentate ligand. So we have a bidentate ligand. So let me draw the bidentate ligand here. So this is the bidentate ligand, that is ethane 1,2-diamine, and one more bidentate ligand I am supposed to draw here. So this is the one more ethane 1,2-diamine bidentate ligand, and this is actually the dextrorotatory molecule, dextrorotatory isomer. This particular compound rotates the plane polarized light towards the right hand side. So don't forget the charge, that is the 2 plus we have. And if you place exactly a mirror in between this compound, and we have a one more mirror image of that, so that would be definitely levorotatory. So platinum we have in the center, and we have a Cl here, mirror image you need to imagine. So this will be the 2Cl what we are going to get if it is a mirror, and exactly the same. And we have En over here. So let me draw En over here. That will be ethane 1,2-diamine bidentate ligand, and we have one more bidentate ligand here. So here I am supposed to draw ethane 1,2-diamine in this fashion. So this is how the levorotatory, and this will be levorotatory isomer what I am supposed to write, and it has a charge again. So the charge will be, I will be writing it for 2 plus. So dextro isomer and levo isomer. So remember that the middle dotted line what I am supposed to draw here, that is the mirror, and we have a mirror image isomers, and they are non-superimposable also. So that is the second example. So we'll see one more example. Using that I am going to explain one more property related to optical isomer. So the example what I am going to consider here is cis of CrCl2 En 2 times we have, and the charge, it has a charge, the charge will be 3 minus. So cis CrCl2 En. So I used already En, that is bidentate ligand. So let me change, I consider this as OX. So this will be the one more bidentate ligand I consider, because OX is also one bidentate ligand. Do you know what is that OX actually? Oxalate ion, C2O4 2 minus, that is also bidentate ligand. So we'll see how actually the cis isomer of this can be drawn. So let me write the one more of the same kind, because I explained both together. The trans isomer of the same compound, that will be CrCl2 and OX twice, and the charge would be 3 minus. So both coordination compound are the same, CrCl2 OX twice 3 minus charge we have, and any complex, but one is cis and one more is a trans. So let me draw the structure and see how actually which one is optical isomerism and which one is not actually. So now let me draw here. So Cr will be the central metal atom, right? And we have a 2Cl and we have a 2 OX. Cis, since the prefix what we have cis isomer. Cis isomer, we have two identical ligands adjacent, Cl, I will write here. We have one more ligand, that is OX. Since OX, oxalate ion, C2O4 2 minus. I hope you know this OX Actually, this is the oxalato C2O4 2 minus. We write in this fashion COO minus, COO minus. So they are going to donate a lone pair of electrons. So bidentate ligand. Therefore, this is the fashion how you are supposed to draw the bidentate ligand. So this is the one bidentate ligand OX, and this is the one more bidentate ligand OX. That is the cis isomer of this particular compound. Now the same compound of trans, let me draw here. So in a trans, the central metal atom is a Cr. As the name indicates, trans, identical ligand should be present exactly opposite. So therefore one Cl I am going to write here, and one more Cl I am going to write, and 2 OX bidentate ligand, and let me draw here, this will be the one bidentate ligand OX, and here we have one more bidentate ligand OX. So this will be cis and this will be trans. So now the question arises, out of these two, which one is optically active, which one is optically inactive? So now it is very important concept, try to understand the cis isomer what we have, and if you place a mirror and we can draw the one more isomer, one more mirror image of this. Okay, and if you draw the one more mirror image of this, and if you place over here, they are non-superimposable. So if you have non-superimposable mirror image isomers, they are optically active. So what I am going to say, the cis isomer is optically active. Then what about the trans isomer? So now let us assume I am going to place a mirror over here, and I am going to draw the mirror image. So since it is trans, we have a Cl, OX, OX is same. But if you replace and this one, and if you place over here, they are superimposable. Remember, in the previous example they are non-superimposable. In this particular example they are superimposable. Therefore this molecule is optically inactive. So I am going to write here, this is optically inactive. Why it is optically inactive? Because there is no mirror image for this one. Since there is no mirror image, therefore they are not supposed to be non-superimposable. They are supposed to be superimposable. Therefore optically inactive it is. Whereas the cis isomer is optically active. Try to understand the difference between that. And one very important statement I am going to explain here. See here, if you have a cis isomer and if you have a trans isomer, only cis isomer is going to show the property of optical activity, whereas a trans isomer won't show the property of optical activity. So this shows the property of activity, this won't show the property of activity because of the only word, remember, cis and trans, whatever the complex it is. If it is cis isomer, that shows optical activity. If it is a trans isomer, that won't show optical activity. The reason I say we don't have a mirror image which are non-superimposable. We have a mirror image which are superimposable, and then there is no question of enantiomer. Then there is no question of optical activity also. So that is how the second type, that is optical isomerism, can be explained. So we have discussed two different types of stereoisomerism. One is geometrical isomerism and one more is optical isomerism. In a geometrical isomerism, cis trans we consider, whereas in case of optical isomerism we consider dextrorotatory and levorotatory. That is all about the concept of isomerism in coordination compounds. Last example is charge species, and you need to mention the charge, that is 3 minus over here, and that is also 3 minus over here, and that I forgot to mention the charge. And now the charge is also very important part, because the given complex is a charge species. If it is a neutral, there is no need to mention the charge. Next theory of coordination compounds is VBT, valence bond theory. I have considered some postulates of that, and in the examples, the rules to be followed I have mentioned here. So we'll see first what are the postulates of valence bond theory of coordination compounds. So remember that this is a VBT related to coordination compounds. So the first postulate, in very short keywords I have written, central metal atom provides vacant orbitals. Central metal atom which is present in coordination complex, that has to provide vacant orbital, so that the ligands are going to donate lone pair of electrons and hybridization takes place and coordination bond is going to be formed. That is the first and foremost very important point of central metal atom. Central metal atom of coordination complex has to provide vacant orbitals. So how actually the vacant orbital is going to be provided? In some cases, in some examples, we have vacant orbitals. It may be S atomic orbital, it may be P or D. In some cases, pairing of electron takes place so that the vacant atomic orbital is going to be generated in case of a central metal atom. The second one, you just see the number of vacant orbitals is the same as the coordination number. So the central metal atom, it provides the vacant orbitals, but it provides the number of vacant orbitals depends upon the coordination number. Central metal atom, if you consider, and how many number of ligands are going to be surrounded. For example, we have a central metal atom which is surrounded by 6 ligands, means the central metal atom has to provide 6 vacant orbitals, because we have a 6 ligands. We have 6 ligands means 6 lone pair of electrons is going to be donated. Therefore, the metal should have vacant 6 atomic orbital to occupy the lone pair of electrons in that, so the coordination bond is going to be formed. So remember that the number of vacant orbitals provided is actually as same as the coordination number in a complex. Vacant orbitals undergo hybridization. The concept of hybridization is the very important one. As we know, when we have atomic orbitals of different energy and different shape, they undergo intermixing to form new orbitals of identical energy. This process we call it as hybridization, and the new orbitals what we get, that we call it as hybrid orbitals. Intermixing of atomic orbitals of different energy to get to get hybrid orbitals of identical energy, we call it as hybridization. So remember that in case of hybridization, number of atomic orbitals involved in hybridization involved in intermixing as same as the number of hybrid orbitals what we get. The vacant orbitals what we have in case of central metal atom, that undergo hybridization to produce hybrid orbitals. The same number of hybrid orbitals is going to produce. Ligands should have at least 1 or 2 atomic orbitals with a lone pair of electrons. As I said, if the central metal atom has a vacant orbital, there must be a ligand which has lone pair of electron for the donation, isn't it? So ligand must contain the lone pair of electrons, and these lone pair of electrons are going to be present in atomic orbitals. We know that one. So how actually the coordinate bond is formed? Very simple manner I have written. The hybrid orbitals, central metal atom provides vacant orbitals. They undergo intermixing to provide hybrid orbitals. So these hybrid orbitals of a central metal atom, they overlap with the filled orbitals of ligand. Ligand has atomic orbitals filled with lone pair of electrons. So these filled orbitals of ligand, they are supposed to overlap with the hybrid orbitals of a central metal atom, so that the coordination bond is going to be formed. Coordination bond we get, and a complex is going to be formed. So this is a very important point. Understand, the vacant orbitals provided by metal atom undergoes hybridization to produce equal number of hybrid orbitals which overlap with the filled atomic orbitals of ligand which contains lone pair of electron, so that the coordinate bond is going to be formed. So it is very important to understand the theory, how vacant orbitals are produced, how hybridization takes place, then it will be easy for us to solve the examples related to that. The last point also, you remember, the type of hybridization decides the geometry of the molecule. What type of hybridization takes place, whether it is sp3 hybridization, dsp2 hybridization. So the based on the type of hybridization, geometry of the complex is going to be decided. So that is all about the postulates of valence bond theory of coordination complexes. So in case of examples, only the theory part is not enough. So we need to know some keywords or some fundamental terms what we use while solving the example. So you need to remember that one. So therefore I have written the key points here. So here in some examples, n minus d atomic orbitals undergo hybridization. In some examples, nd orbitals undergoes hybridization. So d atomic orbital, n minus 1 and n. So let me consider later some particular examples to know how it is n minus 1 and nd. If n minus d hybrid orbitals we have, the complexes what we get in the final, we have a name for that, and that we call it as inner orbital complex. Remember that? If n minus 1d atomic orbital if you consider, we get inner orbital complex. We have two more names for that. You can call it as low spin complex, you can call it as a spin paired complex. You need to remember all the three: inner orbital complex, low spin complex and spin paired complex if you have n minus 1d atomic orbitals. If you have nd atomic orbitals, we get outer orbital complex, we get high spin complex, or we get a spin free complex. All the three names you need to remember. So the complexes what we are going to get after the valence bond theory discussion, we have two different complex: inner orbital complex and outer orbital complex. Inner orbital complex you can call it as low spin complex also. Outer orbital complex you can call it as high spin complex also. Know the name. And this magnetic property, we know that the very important demerit or limitation of Werner's theory is, Werner's theory explains the primary valency and secondary valency, that does not explains the magnetic property of a complex. But here in valence bond theory we have the explanation for the magnetic property of that, and the concept is as same as the previous one what we know. If there is a presence of unpaired electrons in the atomic orbital, that corresponds to paramagnetic nature. If there is absence of unpaired electrons, that corresponds to diamagnetic in nature. And the next part is the most important one. So here I classify ligands into two types. One is strong ligand and second one is weak ligand. So the ligands which contains the lone pair of electrons, which has the filled orbitals, they are going to overlap with the hybrid orbitals, so that the coordination bond is going to be formed. The same ligands I classify it into two types: strong ligands and weak ligands. The examples also I have mentioned: carbon monoxide NH3Cn-. So carbonyl, amine and cyanido are the strong ligands. Similarly fluorido, chlorido, bromido, irido, F-, Cl-, Br-, I-, these examples for the weak ligands. So what actually the strong ligand and weak ligand is going to make in case of coordination complexes, remember that if you have a strong ligand, that pairs up the electron, whereas if you have weak ligand, there will be no pairing of electron. So what actually this pairing of electron and no pairing of electrons? I hope you remember Hund's rule. What Hund's rule says? First, if you have a set of same energy atomic orbitals, we are supposed to fill all the atomic orbitals with one electron each. Then the pairing of electron starts. Identical atomic orbitals, if you consider, the pairing of electron starts unless all the atomic orbitals are filled with one electron each. That we call it as a Hund's rule. But if we have a strong ligands, that ligands are not going to follow the Hund's rule. Even though we have less number of ligands, even though we have more atomic orbitals, and in that case the pairing of electron takes place against the Hund's rule. So pairing of electron takes place against the Hund's rule when we have a strong ligand in a complex. When we have a strong ligand in complex, pairing of electron again Hund's rule takes place. And remember that the kind of complex what we are going to get is inner orbital complex. In short, I will tell you, if we have a strong ligands, we are going to get the inner orbital complex. Exactly opposite will be the one more. Weak ligands, if we have weak ligands, as the name indicates, they are not going to pair up the ligands. So it follows the Hund's rule. So in that case, the complex we are going to get is outer orbital concept. That part is very important while predicting the example. If we have strong ligands, we get inner orbital complex. If we have weak ligands, we get outer orbital complex. And inner orbital complex, outer orbital complex uses n-1d and nd atomic orbitals respectively. And you need to remember some examples for strong ligand and weak ligand. Actually, we have a series, we call it as a spectrochemical series. In that we have all the well-known ligands in increasing order, or I can say decreasing order of ligand field strength, and based on that I consider some as strong ligand and some as weak ligand. So remember that strong ligand inner orbital complex, weak ligand outer orbital complex, or a strong ligand low spin complex and weak ligand high spin complex. And the next point what I have written, as in case of last postulates I said the hybridization of a molecule, the hybridization what happens in case of complex, that is going to determine the geometry of the molecule, and we know some well known hybridization with the geometry. If the hybridization is a sp hybridization, we get linear geometry. If the hybridization is sp2, trigonal planar we get. So similarly, if the hybridization is sp3, tetrahedral geometry we are going to get. If the hybridization is dsp2, square planar geometry we get. If the hybridization is dsp3, trigonal bipyramidal we are going to get. If the hybridization is d2sp3 or sp3d2, we are going to observe octahedral geometry. If the hybridization is d2sp3 or sp3d2, pentagonal bipyramidal geometry we are going to get. So you need to remember this directly so that we can predict the geometry of the complex directly. Remember that the hybridization is going to help us to know the geometry of the molecule, and that is all about the second theory of coordination compounds, valence bond theory. So you need to remember the valence bond theory postulates to understand the example better, and the very important note points, which one is outer orbital complex, inner orbital complex, strong ligand, weak ligand, magnetic property, how does hybridization is going to predict the geometry of the molecule, you need to remember that. So in the next session I am going to solve the examples of valence bond theory in particular coordination compounds.